Okay, so let's look at some cryptographic fundamentals. And in this unit, we'll look at some of the basics around traditional ciphers, encoding methods, the usage of keys, and a few other basic fundamentals that we need to cover before we start to look at symmetric key encryption, hashing methods, and so on. And before we do that, we've probably got to touch base with some of the important people who have been involved in laying down the foundations of our encrypted world. Okay, so it's Bob and Alice, and actually they were defined by Bruce Schneier. And it was Bruce who outlined that we could tell stories in cryptography using characters such as Bob and Alice. And our adversaries, of course, we have Eve and Mallory. And we also have other actors such as Peggy, the prover, and Victor, the verifier. Okay, so Bruce Schneier has laid out some of the characters that we could actually define in cybersecurity stories. But it was Whitfield Diffie and Marty Hellman who laid out a core principle of the Diffie-Hellman key exchange method. In 1978-79, they defined a method that allowed Bob and Alice to communicate and openly and end up with the same encryption key. So Bob and Alice could actually communicate with each other, and in the end they would generate the same key. That is known as the Diffie-Hellman method, and it was created by Whitfield Diffie and Marty Hellman. We've since built on that to create other methods such as the elliptic curve Diffie-Hellman method, but it doesn't change the basic methodology that much. Based on this, the researchers Revest, Shamir, and Edelman came up with the first public key method called the RSA method, and it's still in use today. And basically it uses two prime numbers to create a modulus, and the difficulty is to be able to factorize these prime numbers from a modulus. So Revest, Shamir, and Edelman were the first to come up with a public key method, which was proposed with inside Whitfield Diffie and Martin Hellman's work, but they created the first known publicly available public key method. And with public key encryption, what we do is that we can have two keys, a private key or a secret key, and a public key. And the magic of this is that the two keys work together. One can encrypt and the other can decrypt. As we'll find, there are other methods that are used typically these days, especially with the elliptic curve method. Phil Zinnemann is another person who contributed a great deal to the area, and he pondered why it was not possible to digitally sign emails and also secure them. So his method involved pretty good privacy, and it integrated a method of sending emails that could have digital signatures but also support encryption in there and hashing to show that the message hadn't been changed. It integrated public key encryption into it, but it also used symmetric key. And one of the most popular symmetric key methods that we have is AES. So the PGP method uses symmetric key and also public key to secure the message. And this is based on the Randall method created by Vincent Ryman and John Damon. They together won the NIST competition for symmetric key, a standard for encryption key, symmetric key, and that was defined as AES. Ron Rivest also developed a range of ciphers, the RC suite, and was the one who defined the MD hashing methods such as MD4 and MD5. Okay, so these are just a few of the people who created our encryption methods. So now let's move on and look at some of the basic ciphers that we can have. Okay, so there's early examples of what we would see as encoding methods. So examples of that include smoke signals, the Navajo code talkers, and so on. So in many applications, especially in war and in love, there has been examples of using encoding to be able to keep our messages secret. So overall what we have is we have an encoder and we have a decoder. Then we have our communications channel in between, and we have Bob and Alice. And unfortunately, in between we have Eve. So with encoding, what we do is that we encode our plain text into some encoding format. We'll call it a ciphertext just now. It's not quite cipher, but we encode into a cipher. As long as Eve doesn't know the encoding method, then we can then decode at the other end to take us back to our plain text again. So there are several ways that we can do this encoding and decoding that we'll look at a little bit later. So along with these methods, one of the first encoding methods that we would use is Morse code. And with Morse code we use dots and dashes. So for an A it's a dot and a dash. For a B it's a dash, dot, dot, dot. C becomes a dash, dot, dash, dot. So it was in the time when the telecommunication systems could only support pulses along the line. We obviously need a space in between each of the characters, and then between each of the words we'll have a longer space. And what we see within inside our Morse code is that some of the more popular letters are represented by a smaller code. And some of the least popular ones, such as a J, is represented by a longer code. And this is quite popular within inside our encoding to make sure that we're efficient in our usage of the communication channel. Another method that was used, and obviously isn't that secure, is with polybias. With this we create a grid, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and we can map our letters onto that. And there, quite easily, I, J, K, and now we've got 26 letters, so we'll just overload this one here. Hopefully we'll be able to easily find out whether it's a Y or a Z. So to take the word hello, fairly simple. We look up H and it's 2, 3. E becomes 1, 5. L is 3, 2. 3, 2. And then O becomes 3, 5. Okay, it's quite simple, but you can see here when we see the numbers, if we don't know what the encoding is, could be quite difficult for us to be able to discover how we get back to the hello. So this is really an encoding method, and it's fairly easy to convert from one into another. A more graphical method that we can use to be able to create our ciphers is a pigpen cipher. So in this case what we do is we draw 4 grids, one as an X and O format and the other one such as this. So we'll just easily put our characters in. There we have J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. Okay, that's good because we've managed to fill up all the letters this time. And then what we'll do is that we'll put a dot in each of these to identify each of the grids, and we'll put a dot in that one there. Okay, so it's fairly easy to remember the grid, hopefully. So what we will do is that we can now create our cipher. So let's say we wanted an N. We would draw a square and then we put a dot in it. A becomes this, which is this pattern here. P becomes that pattern with a dot in there, and I becomes this pattern, and then an R becomes this pattern here. N-A-P-I, I've missed out the E, R. So in this way we can actually create a graphical representation of our encoding. Again, if we don't know what the secret coding is, then it might be difficult for us to actually see that this is even a cipher. A more complex cipher is known as the Playfair cipher. So with this we introduce the concept of having a key, and the key is shared between Bob and Alice, and only they will know it, and the cipher is then generated based on this key. So if the key is, say, Napier Uni here, then what we do is we write out the grid using the key. And then we'll put the letters back in that we've not used in there, because we've used I before, so we would not use that one again. So we'll put in B, C, D, we've used E, so we'll go F, G, H, I, J, K, L, M, O, S, T, V, W, X, Y, and Z. So this now becomes our grid for our cipher. And what we do is that we take each of the characters in our ciphertext, such as A, T, T, A, C, K, attack. And now what we do is we draw a boundary around the letter A and T, and then we'll take the opposite of that bounded character. In this case we have M and E. Now we take T here and A again, and we'll take them opposite this time, the E and the M. And finally C and K. So there's a rule that allows us to be able to take the characters which bind these together. So the C and the K becomes the letters beside them. So we end up with a K and a T. So this allows us to be able to code 2 characters at a time into the cipher. And the challenge here is to be able to generate the grid to be able to get to this point here. So one of the ciphers that's been used fairly extensively is the usage of the Caesar cipher. And with the Caesar cipher, we basically just take our alphabet and we shift the letters by a given number of characters. So if we moved by 2, we would end up with this. So a C becomes an A, a D becomes a B, and so on. And as long as Bob and Alice know the number of Caesar's shifts, then it's not too difficult to be able to encode and decode. Unfortunately, the number of ciphers that we can have is only 25 different ciphers. So it's going to be quite easy for Eve to be able to analyze each of the 25 different shifts and to be able to determine what the shift is that has been used. A more advanced version is a scrambled alphabet. And with this, we take our characters and then we will randomly place the mapping of the characters to our encoded value. So let's see, we went for Z and a W there, P, S, B, R, and so on. So B becomes a Z, and D becomes a W, and so on. And then the number of ciphers that we have now is obviously that there are 26 different possibilities for an A. Then for a B, we've already used one, there's 25. And then for a C, 24, and so on. This becomes 26 factorial, and it's a massive number. 4 times 10 to the 26. 4 with 26 zeros gives us the total number of combinations of a scrambled alphabet. So that looks fairly secure. You would think not even the best computers in the world could crack that within a reasonable time. But what we do is that we take we use frequency analysis to be able to understand different patterns within inside the ciphers. For this, we find that E is the most popular character, followed by T and O and A. We find that for diagrams, a T and an H, the word in, are the most popular two-letter currencies. And then for trigrams, the is the most popular one here, ing at the end of a word, and. And the most popular words are the, of, and. So what we can do is that we can go in and we can count the frequency of the single characters, also for two-letter equivalents, or 3, or for words if we can identify a space. And it won't take us too long to be able to do a frequency analysis and work out the mapping of this alphabet to this one. So this is known as frequency analysis, and it's an important technique within inside our cipher cracking principles. One way to overcome this is to use something like a Vigenère code. With a Vigenère code, what we do is that we draw a grid like this, and then we use a keyword. So for our mapping, we have this here, and then we'll move one space to the next one, and so on. Then what we do is we have a code word, just like we had here. Bob and Alice share a code word. So if the code word was BC, then what we do is the first time we'll use this row to be able to do our mapping, and then the second time we'll use this row to do the mapping. And if we have a long enough key, and if the key is secret, then it may be difficult to be able to find the mappings, because in this case a B would relate to a C, but for a C as part of the key now relates to a D. So this will defeat the frequency analysis, but it's still possible if we have enough text to be able to crack this cipher by looking at patterns, common patterns of activity that will repeat. So Vigenère cipher, although it's better than the scrambled alphabet, it can still be cracked with a computer in a fairly short time. If we're looking for a perfect cipher, then we need to look at a one-time pad. With a one-time pad, then we'll have some sort of alphabet mapping. So we have a secret codebook that we have, and we can only use this one time. then what we would do is that we would then use this codebook to send our characters. So if we wanted to send an A, that's 1, 2, 3, 4, 5, 6, we would send a character 6. A W, 1, 2, 3, 4, 5, 6, 7, 8, 9. A W would be 9. So if Bob and Alice can share the same code book, then Alice, when she receives it, just looks up the 6th character and will map it back to the A, and so on. So a one-time pad is a perfect pad, is a perfect cipher, but really we would have to get rid of the code book and try again. Obviously we could have different days of the week having different code books. So on a Tuesday we might use one cipher, and a Wednesday we'll use another one, but we could say vary it with some other parameter. Another interesting cipher is the homophonic cipher. With this, what we can do is that we can take the most popular characters and give them more codes than the least popular ones. So for example, we might say that, and B isn't so popular, so we'll only give it 2 codes. When we write a word, we might go 07, 11, 64, and 31. When Eve analyzes the frequency of all of these numbers, she'll find hopefully that they don't vary that much in the probability. So it's very difficult to spot the more popular characters as we did here. But obviously once Eve finds out what the mapping is, then she can crack all of the messages. So that's the core weakness of our ciphers, is that once Eve finds out the method used, then it can cause problems in that we will have difficulty in changing the algorithm. So let's now look at our encoding methods that we would typically use. With encoding methods, we often start off with plain text, and then we'll convert into some other format. Typically that's hexadecimal or base 64. And really what we have is that these are representations that humans can interpret, where a computer only really understands ones and zeros. Again, ASCII, our characters can be 8 bits or 16 bits. And it's just an interpretation of the bit pattern that's stored that gives us our formats. And we need a way to be able to view our encryption keys and our binary data. So these 2 formats are typically used, hexadecimal or into base 64. Okay, so we go from plain text into ciphertext and then back into plain text again. In crypto, we typically deal with bytes or byte arrays, and we process those byte arrays. Hexadecimal, it's fairly easy. We take 4 bits at a time and we represent them in a hex, as a hex character. We just have to remember how to count up to 16, 15. So a 10 becomes an 8 and a 2, an 11 or a B, and 10 is an A, that's C, D, E, and finally F. Okay, so when we're creating our bit patterns, we'll take 4 bits at a time. So then a bit stream of 1 0 1 1, 1 0 1 0. For that byte, we take 4 bits at a time. That's a 7, and that's an 8 and a 2, which is an A. So that is represented as 7A there. Okay, so every byte we have 2 hex characters. When it comes to base 64, we use a base 64 table. So I won't show all here, but a value of 0 becomes an A, value of 1 becomes a B, 2 becomes a C, 3 D, and so on. And we have a limited character set. Then what we do is that we take our bits 1 0 1 1 1 0 1 2 3 4 5 6. We take 6 bits at a time, and then we encode them, each 6 bits, as a single character. So it's difficult to see from here. That's a 1 2 4 6 8 is 14, 14 and 16 is 30. So that's a value of 30 here, and I think that's encoded into an E. So then with base 64, if we end up with zeros that are missing, we pad into zeros there. So it's 1 2 4 8 16 32, and a 32 becomes a G. So this encoded is EG. But with base 64, we want at least 4 characters, so we pad with equal signs. Okay, so we have padding here to fill up the number of bits into a multiple of 6, and we also have padding here to make sure that we have multiples of 4 characters. And it's often the way we identify base 64 is we look for these equal signs. The way we identify hexadecimal is that we will see this limited character set here with 16 different characters. So that's our basic encoding that we have. Now let's look at the basic operations that we would implement. So we like to keep things nice and simple. So the 2 main operators that we use when we're doing our encryption is typically what's called the XOR operator, and the shift left and shift right. With an XOR, we have a little adder there. 0 and 0 gives 0, 1 and 0 gives 1, and 1 and 1 gives 1 0, but we forget about that, and that just becomes 0. The advantage with this operation is that we never lose anything. We can take our values and XOR it with something. If we XOR with the same thing again, we will recover the original data again. So it's a magical little operator that we can use. The other operator that we use is rotate right and rotate left. Basically, we take the bits we have and we rotate them by moving them a number of places, and then whatever falls off here goes in the other end there. So rotate by 2 to the left would become this, and to the right we'd move that one out to there. So with these 2 basic operations, we can really perform a lot of encryption methods just by doing these and then doing the reverse on the other side. So an encryption method might be XOR with a certain value, shift rotate by right by 2 places, and then to decrypt rotate left by 2 places, and then XOR by the same value. So that's our operators that we would often use. Let's look at another principle, and that's using the mod operator. And with the mod operator, we'll look at that when we look at public key encryption. And basically what we do is that we try to keep things as simple as possible with our calculations, because we end up with very big numbers. So one of the operations that we'll look at is with the mod of a prime number. So the mod operator in Python, you'll see it expressed as a percentage, gives us the remainder from a divide. So if we have 15 mod 4, okay, that becomes 12, that's equal to 3, because we end up with a remainder. So that becomes 3, remainder 3. So it's the remainder part that we're interested in. And the magic of the mod operation is that we can constrain our numbers between 0 and p minus 1, and also that the operations that we will do, such as add and subtract, still work out. So it's a very important operation. If you're interested, we typically call it a finite field. And the finite field is just defined by this prime number. So prime numbers are really important within cryptography. Now the concept that we have is to use different formats for our characters. So ASCII uses 8-bit formats. So a typical one is that an A is represented by 41 hex. Okay, that's a 4 and a 1. We often define hex with a 0x. We can also define this in octal, where we take 3 bits at a time, and as an HTML character, 65 semicolon. Okay, so there are different ways of representing our characters in an ASCII format, but we can also use UTF-16, and that uses 16 bits, so we have a larger character set from there. So for example, an A in UTF-16 is 0041, because we're using 16 bytes there. One area that's important in cryptography is the usage of big integers. In some areas we will take g to the power of x, and we'll end up with a very large number, and even if we take a mod p, then it becomes very large. So in most programs we have 32 bits or 64 bits, but in cryptography, especially in RSA and areas like that, we can end up with 1024 bits, 2048, and even 4096 bits. So for this we use big integers, and with big integers we normally represent them in some form of string, so that we can represent any value that we want and we can still use it. Inside the program, we then use methods to be able to multiply or subtract. So we can't use normally the normal operations to do this. Luckily, Python is excellent at dealing with big integers, and we don't have to use these extended methods. Python automatically knows when we have large numbers. So we can easily multiply these very large numbers and define them, and we don't actually have to use anything different with the operations. So Python is a very powerful language for implementing big integers. Another core method that we have is the usage of random numbers. And with random numbers, we can either have pseudo random or we can have true random. A pseudo random will repeat after a given time and are deterministic and periodic. So we could use this in terms of a simulation or modeling if we want to create repeatable results. For true random, we would use that in terms of a lottery to make sure that the random numbers that we're creating were truly secure. And examples of this include keystroke analysis, how someone uses the keys, and examples of this are the operations inside a computer. Electrical noise is one example of a true random number. Okay, so that's our random numbers. And now finally, before we move on to the next topic, which is symmetric encryption, we'll look at the concept of key-based encryption. So we found the weakness of some of these ciphers is that if we use an encoding format, then Eve can easily discover that. But if we use a key, it becomes more difficult for Eve to try and discover the key that's been used. So in most cases with encryption, what we use is key-based encryption. And for that, we create a number of bits to represent our key. So in this case, if we had 4 bits, then we would end up with 16 different keys, 0 to 15 here, or 2 to the power of the number of bits in our key. So the larger the number of bits that we have, the more keys that we can have. If we have 20 bits, then that gives us 1K, 1024 different keys. Sorry, we have one meg. For 10, we have 1K or 1024. For 20, we have 1 million or 1,048,576. A key breakpoint is at 72 bits because this is around the cracking level of the internet. And if you're interested, it's 4 times 10 to the 21, very large number of keys. But because of computing power, it's possible within a reasonable amount of time to find a key in this space. But if we went to 73, it gets doubly as hard, 74 double, and so on. So we should be able to see that 128-bit keys are so far away from the cracking level that this should be actually secure. Okay, so we'll go on to this principle in a bit more detail in the next presentation. But overall, what we've managed to do is that we've covered our basic encoding methods that we have. We've covered some of the traditional ciphers and the weaknesses of them, looked at the basic encoding, the operators, a little bit of random numbers, some big integers, and also the basics around key-based encryption. Okay, thank you.